Hello everyone, this is chapter 10.1 where we'll be discussing matrices and systems of equations. And first off, I just want to get the ball rolling by talking about what a matrix is. And let me just say that a matrix is an array of numbers arranged by rows and columns. So basically we'll have these brackets. Some books use parentheses, but our book uses brackets. In fact, I prefer using brackets as well. And then we have these numbers here. The dimensions of a matrix is just the amount of rows by the amount of columns. So here we'll have m rows and n columns, for instance. And the notation I'm using here is a little funny and one to get kind of used to. But for instance, we have like a double subscript here. So A11 means that this entry is in the first row, first column. And for instance, A22 means it's in the second row, second column. So the first number represents the row that it's in. So first row, second row, all the way to the nth row. And the second number in the subscript means what column it's in. So here it's in the first column, second column, and then the nth column. So just to kind of get an idea. Now, that notation really I won't be using too much. It's a little kind of formal. But if you want to get a handle on that, you can try your best to figure out what these are. So for instance, negative 1/2 in this case is A22 because it is in the second row, second column. Negative 4 would be A23 because that's in the second row, third column. But again, that's a little beyond what I want to discuss. And now as far as the dimensions go, let's see if we can find the dimensions of these matrices. A matrice, by the way, is plural for the word matrix. So here there are 2 rows and 3 columns. So this is a 2 by 3 matrix. Remember, row first, then column. So row is the horizontal lists, columns are the vertical lists. So there are 3 rows here and 4 columns, so this is a 3 by 4 matrix. Perfect. So now we'll move on to something a little different, and we'll actually discuss the benefit of using this new notation with matrices now to better handle systems of equations that we saw in chapter 9. Alright, so here now I go on to say that an augmented matrix is the matrix whose entries are coefficients of a linear system of equations. So now we can actually apply matrices to systems of equations and get a matrix from these. And this is known as the augmented matrix of that equation, of that system of equations. So what I'm going to do now is I'm going to take these 3 examples here and I'm going to convert them into matrices. So I'm going to find the augmented matrix. Whenever I do that, I always entitle the arrow as AM, of course, for augmented matrix. So let's see if we can figure out what's going on here as far as that's concerned. So for the first system of equations, so I just wanted the M to look clear. Okay, that's fine. So for the first system of equations, we'll end up getting a 2 by 3 matrix whose entries for the first row are 2, 3, 4, and whose entries for the second row are 3, negative 1, 2. So really what I'm doing is just looking at the coefficients of each of the variables and then writing those as entries of the matrix. Now there are a little bit of decorations we can honestly apply here. One is the so-called equal to bar, which separates the x and y coefficients from what they're equal to in the system of equations. And we can also label these columns by the variables that they correspond to. So notice these are the coefficients of x, where these are the coefficients of y. So we want to make sure we have things lined up in that specific order first, so that we can convert to an augmented matrix in a very standard way. Now for the next one here, notice there are some things missing, so let's see how that affects the augmented matrix for this system of equations. So let's see. So for the first row, it's not too bad, it's just 1, negative 1, 1, 3. Let me space it out a little bit, 1, negative 1, 1, 3, and our bar would be here, that I guess I'll do in black, that's fine. Now our second equation will correspond to the second row. And remember, we have an x column, a y column, and a z column. Now the x coefficient is 1, that's fine. The y actual coefficient is 0 because y is missing here. So we can write this as 0y, so its coefficient is 0. Z's coefficient is 2, and then that's equal to 5 on the other side of the bar. Great. And now for the third row, finally, x is missing now, so that's 0 for x, 1 for y, and negative 1 for z, and it's equal to 11. Great. Now, the funny thing about this is so far we haven't actually seen any insight as far as how this is helpful to solve a system of equations. So far, it's just kind of shorthand in some sense. It's less to write. And that's the biggest motivation for matrices at first glance, is just writing less. And then we can apply the same methods, actually, I'll reintroduce those to us right now in the next screen. But the biggest indicator, I think, of when you stop, as far as how we know we arrived at a solution, is this. Because this system of equations, two equations, is really the solution to a system of equations. Notice the solution is just 5 comma negative 3. X is 5 and y is negative 3. Now, what this corresponds to as far as an augmented matrix is concerned, though, is the following. So remember, we have an x column, we have a y column, and then we have we have an equal to bar. So now notice here, there is 1 in front of x, there is no y, and it's equal to 5. So this corresponds to x equals 5. For the bottom, we have 0 x's, 1 y, and is equal to negative 3. So this is our indicator that we've actually finished, and our solution will be x equals 5, y equals negative 3. In fact, this is really the goal when using matrices to solve system of equations. So if you recall in chapter 9 how we handled solving systems of equations, one way we got to, in fact, when we discussed 9.3 specifically, one method that we used, Gaussian elimination, was that we started with a system and we would write equivalent systems, so we would replace equations until we had a particular form we liked, then we would back substitute to find a solution. So here, with matrices, we'll be doing something similar. We'll be starting, of course, with a system of equations, develop an augmented matrix, much like we did here. Then we'll apply row operations, much like we applied those operations for systems of equations, to develop equivalent matrices. And then we'll do that up to the point where we have something like this, that we can just blatantly read out what the solution is. So now let's take a look at those row operations and an example of how we apply those to solve a system of equations. All right, so here are the row operations. There's 3 of them. And again, if you look at 9.3, the operations I gave you for finding equivalent systems is really this, but now in the context of rows of a matrix. So here I say we can interchange any 2 rows. We can multiply a row by a non-zero constant. And then finally, we can replace any row by the sum involving that row with a constant multiple of another row. So basically, with 2 and 3 combined, you can essentially get what is called a linear combination of any 2 rows and replace either of those rows involved in that linear combination with that result. And a linear combination, by the way, is just a constant times something plus a constant times something else. So if you want to take a linear combination of 2 rows, you multiply them by numbers and combine them. That's a linear combination. I won't really be using that phrasing too much in this class, but that is something in the grand scheme of things that kind of happens as far as these are concerned. Now, as far as notation goes, while interchanging 2 rows, let's say we want to interchange row I and row j. So this is the notation for rows. So here we'll actually have 2 rows. So it'll be row 1 and row 2 only. But in general, you'll have maybe like row 1, row 2, row 3, row 4, and so on. So r sub I and r sub j just means that this is the ith row and this is the jth row. And this double arrow here just means we're interchanging those rows. So row I becomes row j and vice versa. So you just swap those rows. Okay, multiplying a row by a non-zero constant would be to replace row, let's say I, by k times row I. So we're replacing k times a row. Well, we're replacing a row by k times that row is what I meant to say. So the arrow denotes what it replaces. And then this one would be something like this. This would be, let's say, rj plus a constant times ri, and that'll replace rj. So you add a constant of some other row to a row, and that replaces that row. That's what the third one says. So now let's see if we can get a handle on these row operations in turning an augmented matrix into that goal I was talking about earlier from the last example we saw, where the leftmost square was 1, 0, 0, 1. So first off, the augmented matrix for this particular system of equations is, let's see, 3, negative 2, 5 for the top row. Good. 5, 3, 2 for the bottom one. Great. And here we have row 1 and row 2. And I want to apply row operations. And it gets a little weird because we don't really know what we're doing at some point. Kind of have to figure out and feel around. But remember what our goal is. Our goal is to get zeros involved. In fact, our biggest overall goal is this. Because this implies that x is equal to the top number and y is equal to the bottom number. So how do we get to this point? Well, it'd be nice to have ones in place, but to be quite honest, the ones can wait. The more important thing here are the zeros. So we want to get zeros in place. I want a 0 here and a 0 there. This is our line, of course. Good. So now, how do we get a 0 in the first column? Normally you want to go column by column is kind of the suggested, guideline here. And to get a 0 here, notice we can multiply the top by 5, bottom by 3, add those together, and then we'll get a new row 2. So that's what I meant by linear combination. In fact, really what we're going to do is take that linear combination of R1 and R2 and use that to replace R2. So let me kind of erase this goal for right now. We'll get to that sooner or later. And this squiggle tilde symbol will just denote equivalent matrix. So now the top row in the matrix will stay the same, 3, negative 2, 5. The bottom row will be replaced with, again, there's a few ways of doing it. If you wanted to use these operations as is, then you'd have to multiply it by 3 first, so this becomes a 15. And then after doing that operation, which is operation 2, then you can add negative 5 times row 1 to row 2. That would be using the third operation. But in fact, we can just combine those in the linear combination way I said before. So to get from here to here, what I'm going to do is I'm going to multiply negative 5 to row 1, add that to 3 times row 2, and this in total will replace row 2. So this right here is the operation we're using that will get us from this matrix to this matrix. Now the actual work here, so this is our instruction, the actual work here I'll do off to the side, but that'll be erased afterwards. These instructions can regenerate the work as needed. So negative 5 times row 1 is going to be negative 15, positive 10, negative 25. 3 times row 2 is going to be 15, 9, and 6. When you add these together, we get 0, 19, and negative 19 actually. 0, 19, and negative 19. Now I don't want to jump the gun too much, but notice that in the bottom, they all have 19 in common. So we can divide by 19. So in fact, one thing we can do really is if you wanted to write it all in one step, you can write multiply by 1 over 19, that would be combining step 2 again, or operation 2 again, and then that would make this 0, 1, negative 1. But just so I'm not jumping the gun too much, I'll actually show that in one additional step here. So going from here to here, we have 3, negative 2, 5, and then 0, 1, negative 1, because for this operation going from this matrix to this matrix, I am multiplying 1 over 19 to R2, and that replaces R2. That's our operation there. Perfect. And that again is step 2, the second operation. Great. Now at this point, to be quite honest, if you want to convert this back into a system, we solved for y already. Y is negative 1, and then you can back substitute. So what I'm describing, of course, is Gaussian elimination, and in fact, if you write this as a system of equations now, you'll notice this is in what we called a not reduced, but it was a row echelon form. That's what we called it last time. Otherwise known as upper triangular form. So you can kind of see what it would look like when you have more than 2 equations. we would have this lower triangle of zeros. So in the case where you have 3 equations, there'd be 3 zeros like this. So one here, and then one next to it like that to form a triangle of zeros. So that's what's known as row echelon form. But reduced row echelon form is where we kind of go full Monty, so to speak, in the sense that we get that goal I was talking about earlier. So to do that, actually, remember, we want this to be 0. So we're going column by column. The first column, we made this one 0, perfect. And now onward to the next column to make this one 0. Well, notice all we need to do is multiply the bottom row by 2, add it to the top row. So let's see if we can apply that operation here. So I want to add row 1 to 2 times row 2, and that'll replace row 1. And remember, you can replace any of the rows so long as it's involved in that linear combination. Good. Now here I don't think I'm going to write out the work too much, but notice row 1 stays the same, and row 2 is multiplied by 2. So if you add those together, 3 plus 0 is still 3. If this is multiplied by 2, this becomes 2 added to negative 2 is 0, so it makes it 0 like we wanted. And this times 2 is negative 2 plus 5 is 3. And notice on the bottom we still have 0, 1, negative 1. That hasn't changed. Great. And now we're kind of done, because the last step really is to just divide the top by 3. I don't have too much space to show that actually, but I guess I'll write it here. So this is equivalent to 1, 0, 1, 0, 1, negative 1. Like that. I hope that makes it good, yeah? And really what we're doing from here to here is we're multiplying 1/3 to R1, and that replaces R1. So that again is the second operation. And now we're done because we have our goal. So notice this really just means if you convert this back into a system of equations, it means that x is equal to 1, y is equal to negative 1. So now this implies that our solution is x equals 1, y equals negative 1. And if you wanted to, you can check that with the original system of equations. Notice when you plug in 1 for x and negative 1 for y, this becomes 3 plus 2, which is 5. This becomes 5 minus 3, which is indeed 2. So this seems to work. So now we'll look at something a little more complicated. Now finally we're going to do a system of 3 equations this way. It's going to be a little complicated, like I said, but that'll end the video after that. So let's take a look at that right now. Right, so like I said, I wanted to do this example, which is a pretty full system of equations with 3 variables and 3 equations, of course. So let's start off by finding the augmented matrix and just jump right into it. So the augmented matrix here, of course, is going to be 3, negative 2, 1, 15. Kind of space things out a bit so we don't get too confused. And second row is going to be negative 1, 1, 2, negative 10. And then we'll have, let me make that a little more clear, sorry. There we go, good. And then we have 1, negative 4, and 14. Perfect. So now what I want to do again is I want to apply row operations so that we have zeros. Now the goal for a system of 3 equations is a little harder to grasp, but once you understand the pattern, it'll be kind of obvious. So we want only x in the first row and then equal to a number, only y in the second row equal to a number, and then only z in the third row equal to a number. So this is our goal for a system of 3 equations. And as you can kind of tell, you can see what this will look like for any number of equations in the system of equations. Because really it's just a diagonal of 1s and the rest are 0 for the leftmost square. And that's kind of what we're going to be focusing on. So good. So with that being said, remember we want to go column by column. So first column, I want these two to be 0. But let me just kind of think a little bit here. I guess that's fine. I was going to say let's interchange row 1 and row 3 so that we have a 1 on top. But remember, the 1s will come on their own time. Let's focus on the zeros first. So how do I make these two each 0? Well, we could multiply the top by 1/3 and then add it to each of these, but then we'll get fractions involved. And in fact, that the first thing I said was that we would do something to the one that's not circled and then apply that to each of these one at a time. And that's really what we're going to be doing. So I'm going to basically combine row 1 with row 2 and row 3 one at a time. But I'm not going to be multiplying by 1/3. I'm going to be multiplying row 2 and row 3 each by 3 or -3 to combine with that 3 on top. So let's see if we can figure that out here. So for this first operation, I'm going to actually do 2 operations at once. But notice row 3, or not row 3, but row 1 is going to be untouched. So row 1 will stay the same. It'll stay 3, -2, 115. And what we're going to be applying to this matrix to get to this new matrix now is I want to multiply row 2 by 3, add that to row 1, and that will replace row 2. That's the first operation I want to use, but I'm going to be applying 2 operations in one here. So the next operation I want to use, it will involve a different row actually, is with row 1 and row 3. So if we multiply row 3 by -3 now, in fact, let me write it like this. Row 1 minus 3 times row 3, that'll replace row 3. Now you can always do more than one operation at a time if you'd like. At first hand, to begin with though, it's best to just to do one operation at a time, to be quite honest. So this may be overstepping my bounds as far as kind of giving you too much at a time, being a little overwhelming. But notice that when you apply an operation to row 1 and row 2, but it only replaces row 2, row 1 would be the same after that operation. So if you apply another operation at the same time that involves the row that hasn't been messed with, in this case row 2 was the one being replaced, but this operation doesn't involve row 2 at all, then it's actually okay. So it's something to keep in mind, and if you want to do it one step at a time, you can. That's okay. So now let me erase this goal here, and let's see if we can apply the work for these instructions. So row 2 times 3, there we go, is a -3, 3, 6, -30. That's 3 times row 2. Adding that to row 1, that's 3, -2, 115. And our result is 0, 1, 7, and then -15, which sounds kind of not too great, but that's okay. Perfect. And now for the second operation here, we're going to do row 1, which is 3, -2, 115, perfect, times, well not times, but -3 times row 3. So row 3 is going to be multiplied by -3, and that'll give us -3, +3, that times -3 is +12, that times -3 is going to be, let's see, I guess 42, -42. Perfect. Adding these straight down gives you 0 here, 1 here, 13 here, and let's see, what's 42 minus 15? I think it's 27? Yeah, so it's going to be -27. So we get this. So if you kind of think about what we've been doing here, if you convert this back into a system, it's not hard to see that basically the bottom 2 equations will only involve y and z. And in fact, a method I showed you in 9.3 was that you can eliminate a variable 2 different ways, which we've kind of done here, and then solve the leftover system. So we can solve this remaining system for y and z and then plug that back into the original, or one of the original 3, to find x then. So just to kind of keep in mind, a lot of the same ideas are kind of floating around, but just with different interpretations. So now we're going to, well, we're done with the second column. Now we move on to the, we're done with the first column. Now we move on to the second column. So now I want these 2 to be zeros. If you remember the goal, the zeros were here, here, and up here. So that we have a diagonal of non-zeros only. Good. So now notice the one that is not circled is, well, the second one in this case. And that's the one I want to use. I want to use this second row with each of these one at a time in our operations, because that one will be unchanged. So notice here, from here to here, the top one was unchanged. That's one we arrowed. The one that was did not have zeros. Here, the one that will not be zeroed out will be the second row. So So that one will actually be unchanged as well. And as you do this more often, you'll kind of realize these patterns more. They'll be more coincident. Good. So now what I'm going to do here is to zero this out, I need to multiply row 2 by 2. So this will be 2 times row 2 added to row 1, and that'll be the new row 1. What about for row 3? Well, if you multiply row 2 by -1, so -1 by row 2, and then add that to row 3, that will give you the new row 3, because that'll cancel out this 1 and make it a 0. So now let's apply these operations one at a time and see what happens. So 2 times row 2 is going to be 0, 2, 14, -30. Adding that to row 1, 3, -2, 1, 15, will give us, let's see, we get 3, 0, 15, and this is -15. Good. So that's the new row 1. 3, 0, 15, -15. Great. Notice they all have 3 in common, so I really want to just divide by 3 right away, but I'll leave that for the next operation. And now for the second operation down here, -1 times row 2 will be 0, -1, -7, +15, because we're negating each entry. And then plus our 3, which is 0, 1, 13, -27. And this should give us 2 zeros here, notice. 0, 0. Meaning z will be solved for after doing this. So let's see. So 13 minus 7 is 6. And then 15 minus 27 is going to be -12. So this is 6, -12. So again, I really want to divide by 6 here and just get 1, -2, meaning that z will be -2. But I'm going to save that for the next operation. So just to erase the work here real quick, I'm going to clean things up by dividing by whatever they have in common. And I notice a good place to do that is right now. Because in fact what we can do is we can, well, replace row 1 by 1/3 row 1. And very similarly replace row 2, row 3 by 1/6 row 3. Perfect. So what we end up getting is the top one divided by 3, which is 1, 0, 5, -5. Bottom becomes 0, 0, 1, -2. And the middle one actually stays the same, 0, 1, 7, -15. And we're almost there. In fact, at this point, we're in row echelon form, meaning we have that lower triangle of zeros already. In fact, we would have been in that form even if we didn't do this this top operation here. We only needed a 0 here to get in that form. So at this point, you can convert back into a system and apply back substitution. But I want to go through it all and get row reduced, or reduced row echelon form, so that we have a diagonal of only 1s and the rest are 0 in that leftmost square. And we're almost there. The only thing we need to do now is make these 0, and it's actually very easy to do that because you'll see that the one we're not zeroing out is the bottom row. And if you multiply this by -5 and -7 one at a time and combine with row 1 and row 2, then you'll actually get the result we want. So now finally, let's see if we can follow. So I'm going to multiply row 3 by -5 and add that to row 1. That'll be the new row 1. That's our first operation. Good. The second operation we're going to do is we're going to do row 2 minus 7 times row 3. And that'll be the new row 2. Good. So the one that's not changed only is the bottom one. So the bottom one is still 0, 0, 1, -2. Perfect. Now, again, we could show some work here, so let's do that. So row 1 is still row 1, so it's 1, 0, 5, -5. And then -5 or 3, that's going to be 0, 0, that times -5 is -5. -2 times -5 is 10. So notice when you combine these, you get 1, 0, 0, and that's 5. So we get 1, 0, 0, 5. Good. So this tells us right away x is equal to 5. There's nothing to divide by because there's a 1 there. That's great. And now the second operation we need to do need to do is row 2, which is 0, 1, 7, negative 15. Again, have these spaced out so that you don't get confused thinking there's like a 17 or something like that. And then negative 7 times row 3 is going to be 0, 0, negative 7. Negative 7 times negative 2 is 14. These combine to 1, 0, 0, 1, 0, negative 1, just like that. And we are actually done. So let me erase the work here. And again, you can always use these instructions to regenerate the work, which is nice. And what this tells me now is that x must be 5, y must be negative 1, and z must be negative 2. So our ordered triple solution is 5, negative 1, negative 2. And you can check that on your own. I'm not going to check it. I'm done. But again, I showed the process here of converting this into row-reduced echelon form, or I guess it's called a reduced row echelon form. I always call it the other way around. But the acronym for this is RREF. And in fact, if you have a TI-83 Plus, what you can do is you can actually, in other calculators have this feature as well, you can press matrix, which is second x to the negative 1, so second x inverse. You can create a matrix. You'd have to get the dimensions right. So in this case, it's 3 by 4. Input these entries. You would exit the screen, go back to matrix, and under operations, somewhere down the line at the bottom, you'll see RREF. Select that, and then select RREF of the matrix you just created or edited. So you go back to matrix, select that, press enter, and it should give you this in row reduced echelon form, or I guess reduced row echelon form. I keep saying it wrong. But anyways, that concludes 10.1, and I'll see you in the next video for 10.2, where we'll be stepping a little bit away from systems of equations and then looking more at matrices as objects and seeing what we can do with those as far as combining them together using addition, subtraction, multiplication, division, that sort of thing. So I'll see you in the next video for 10.2. It'll be pretty interesting. Thanks for watching. See you then.